So we have gone through several topics now. One of the last topics that we went through was coherent demodulation. Of AM signals with amplitude modulated signal. Then we found that this was no good, and then we went through envelope detection. This is expensive. This is cheap. Okay. Cheap means that you can do that with very simple equipment, whereas if you were to do coherent detection, you need more expensive equipment. Just let's go through coherent demodulation quickly and see what actually it does. So you have a signal that you send in, okay, then you multiply by cos omega c t, the carrier frequency, and then let it go through the thing. And what happens is that you go through a channel. Channel might be just your terrain. Okay, you have to send signals from here to a long distance, and then when you have signals coming back at you, so over here you have something like ft cosine of omega ct. And then what happens after it goes through the channel is that it goes through some sort of an attenuation and time delay. It goes through this kind of process, okay? And then you have to change this signal back into something that looks like f of t. So what you do then is to multiply by cosine of omega c t minus t naught, and then go through a low pass filter, and then out comes something that looks like f of t. Okay, something that looks like k f of t minus t naught or something like that. So what happens is that when you modulate, if you have f of omega that looks something like this, when you modulate, you create an upper band and lower band, because when you modulate, you multiply something by a carrier. This is the same as doing frequency shifting. So this would Fourier transform to f of omega minus omega c plus f of omega plus omega c with a factor of half. Because this thing is half e to the j omega ct plus half e to the minus j omega ct. Okay, so modulation is similar to multiplying by this phase factor. Multiplying by this phase factor is like doing frequency shifting, and then you have a factor of half because of the cosine there. So what happens then is that the signal, say if this signal looks something like this, and it gets shifted two ways, it creates an upper band and a lower band, minus omega c, and the amplitude, if it starts with 1, it becomes half as tall after modulation. Okay. Then of course if it gets delayed, what does delay do to a signal? If it goes through propagation from here to Chicago or from here to maybe downtown Champaign, you just go time shifting. Okay, what does time shifting do to the Fourier transform of a signal? You just add a phase shift. Okay, just add a phase shift, So we don't worry about the phase shift when we do this kind of plot because we always do amplitude plot. The phase is here. So when it comes out here, it's pretty much the same as it was there. The bandwidth, the frequency plot is almost the same as it was there, except for a phase, except for the amplitude shift. But when it comes out over here, okay, we multiply by omega c, we get this thing over here. Okay, so what happens is that every time when you multiply by omega c, what it does is that it introduces a frequency shift. So you can think of this thing being shifted 2 times over, one to the right and one to the left. And so when you take this picture, like here I was shifting it 2 times over, one to the right and one to the left. And now if you take this same picture and split it 2 times over, and if I have it shift to the right, okay, frequency shift of that signal to the right will give me something like this. Okay? And I take the same signal and frequency shift to the left, I will get something like this. And then one that is exactly right on top of this signal, so it makes this signal twice as full. And it makes that signal twice as full. But then every time you modulate, you introduce a factor of half. So this becomes 1/4, this becomes 1/4, and then this becomes half, because it's twice as full. Okay? So, here is what demodulation do. This process here is demodulation. Demod. Okay? And so when you pass through the low pass filter, you get this. You might have a factor of k that you want to put in because of the attenuation. Okay? So what comes up here is actually this with a phase delay. Okay? With a phase delay. Is this process clear? Modulation and demodulation, yes.
So when you multiply by cosine the second time, it shifts each of those 2 peaks from the first one individually, and then stuff ends up back in the center?
Right.
Okay.
Right, you can pictorially think of it that way, rather than go through the math. You can also go through the math, expand this in terms of trigonometric identities, and then figure out what each term does. There will be 4 terms here. And that is what happens to the 4 terms. Okay, 2 of them superimpose on top of each other. 2 of them were shifted to the right and the left. Okay, what's your name, please?
Mark?
Martin?
Mark.
Mark. What's the last name?
First prime?
Okay. So that is what actually happens, and then this is what you have. Envelope detection is different. This is expensive. Expensive because you have to have this demod signal delayed properly, and also the frequency take to be right so that you can demod the signal. Envelope detection is much cheaper. So what you do is a trick that if I have any signal f of t, I know that if I modulate this signal with a cosine, it becomes a big mess. It looks kind of messy. So instead of directly modulating this signal with a cosine, a carrier, I shift it upward so that it never became negative. I add a DC term to it so that this is ft plus alpha. This is the t-axis I'm plotting. Okay. Now I modulate this signal. Then if I were to modulate it, then I would have something that looks like this. I just have the cosine oscillating nicely somewhere in between. Okay, so this would be f of t plus alpha times cosine of omega ct. Whereas if you were to modulate the thing, you will have some sign confusion. Something will turn negative and something will turn positive. But the cosine itself turns negative and positive. But if I have it modulated this way, I know that my signal is always having a positive sign. Any negative signs that I have comes from the cosine signal. So I can do a detection. There are two ways to do the detection. One is to use a simple diode called a half-wave detection. The other one is to do the full-wave detection. Then what you do then is actually to convert this into its amplitude. So you convert everything that is negative there into a positive sign. So if I replot the whole thing, everything that is negative get inverted to be positive again. That is called full wave detection. You get a signal that looks something like this. The envelope, I didn't draw it well, but the envelope is supposed to be the same. Okay, this is called a full wave detection. And the half wave detection is just to lop off the negative part. Okay, they just do a half-wave detection. You don't worry about it when it goes negative, just set it to 0. This is a lot cheaper to do. Okay, you got a signal that is not magnitude, but with some of the parts missing. But that is okay. Okay? And this is half-wave detection.
Is that fourth function of the ECE2?
What is that?
It says f of alpha plus alpha. Should it be
F of t, yeah, sorry, F of t. Okay, so this is a full wave detection. So, what happens then is that a half-wave detection can be done quite easily. That if the signal comes in, I have a diode. Okay, so if the signal is coming in like this, then after it goes through the diode, only the positive parts go through. The negative part gives me zero current. Okay? If, however, I do the same thing over again with a full wave detector, the circuit diagram would look something like this. I think it looks something like this, okay? I'm just drawing it from memory. So I think it has to go something like this. So if the signal is going this way, then it will go like this. Okay, if the positive current goes like this, the signal will go like that. If the current goes the opposite direction, then it has to go in this path. Okay, let me see. If it goes like this, then it goes like this. Okay, if it goes in the opposite direction, then it goes like this. So the current is always positive in the middle resistor because of the diode. Diode is something that gives current flow in only one direction. So this is the full wave detector. Okay, so then the textbook went through the math of analyzing this. What is the Fourier spectrum of this signal? So the math is quite complicated. And if you like to go through the math, I can go through that with you. Okay. So, so the math goes something like that, that at this stage, the signal that you have, so the received signal that you have is ft plus alpha magnitude, let me put the cosine of omega ct over here. But this term is always positive. The first term is always positive by design. You elevate it with a platform so that it's always positive. So that you will take the magnitude of two signals. I can leave the first term the way it is without having to put a magnitude sign over it. Then I only need to put the magnitude sign over the second term. Then I analyze the Fourier spectrum of the second term in terms of Fourier harmonics. The second term, if I were to look at what it looks like, it's just a cosine omega with everything turned positive. And this is how it looks like. And it's just actually your cosine omega t flipped around. Every time it turns negative, I just flip it around. Okay? So if the original signal has a period of t, the carrier has a frequency or signal of t, the period of this periodic signal becomes t over 2. And you see that? The signal flipped around with the full wave detector will have twice as high a frequency as the one the original carrier has. Can you see that? Okay, so you do a Fourier harmonic analysis. I think this is one of your homework problems, right? How to Fourier analyze the first signal. It's part of your homework. And for those who have excellent memory, you may even be able to spit out a solution for me. Okay? So, again, you can Fourier analyze in terms of the exponential form, the trigonometric form, and a compact form. So you have three formulas to deal with. And then I will just quote you the answer. Okay, the answer is that this one can be Fourier analyzed. It has a DC term, and then it would have the Fourier harmonics from 1 to infinity an cosine of n 2 omega naught t. 2 omega naught because the frequency, if this thing has the frequency of 2 pi over t, this one will have a harmonic of 2 pi over t over 2, which is 2 omega naught. Okay, the fundamental frequency of that is twice as high, so you have this kind of Fourier analysis. And I wouldn't go through finding that A sub n for you. I presume you know how to do that. All of you know how to do that. And so the effect of this thing, okay, the effect of this thing now is just to, if I call this, the textbook called this PT. Okay, PT will consist of two components, P1 and P2, and P1 T is just the original signal multiplied by f of t. Okay, so P1T will be A0 over 2 f of t plus n is to the 1 to infinity an f of t cosine of n to omega naught t. P of 2 of t is just equal to alpha cosine of omega ct. Okay, this P1 of t is actually f of t times cosine of omega ct. Okay, P1 of t is just this term and this term. Okay, this one is P1. The other one is P2. Okay, those are the two things over there. So, P2 of t is not very interesting. It's just the original signal I have over here multiplied by alpha. Okay, it's just this thing multiplied by alpha. But it's this term that's interesting. It contains the signal that I'm interested in, signal that I've transmitted over the channel. Okay, so if I Fourier analyze that term by term, I know that the DC term, the first term, not necessarily the DC term, will contain f of t, but what do the other terms do to f of t? What does this do? This term do to f of t? F of t times cosine of 2 omega naught t. What does it do to the spectrum? So if I look at the spectrum, say f Fa of omega t, which is given by a Fourier transform of this to omega naught t. Okay, if the Fourier transform of this I call Fa of t, the spectrum of this would be just the spectrum of A times these two things. Okay, so it will be just right shifted and left shifted. And what is this shifting frequencies that I have over here? So if I look at n equals 1 term, there should be an n over here, I'm sorry. There should be an n over here. This is n equals 1 term. Okay, I'm looking at n equals 1 term. Okay, so it gets shifted to the right and shifted to the left. How much does it get shifted to the right? 2 omega naught. Okay, very good. So it gets shifted 2 omega naught here, and then minus 2 omega naught here, and then its amplitude that diminished by half. Okay, that's what modulation does. Exactly the same as what modulation does. And then the other harmonics were shifted further to the right. Okay? And so this term does not produce anything in the low frequency regime. Only this term has something that is in the low frequency regime. Okay? The second term is entirely coming from here, times alpha. It does have something in the low frequency regime, but what is it? What is it? It's just a DC shift. It's constant. So it's pretty uninteresting too. Okay? And the other one are just higher Fourier harmonics that goes outside the low frequency band. So if I take this signal P1 and P2, sum them together, P1 is this signal, P2 is that signal, and essentially if I take my PT, pass it through a low pass filter, what do I pick up? I pick up this term plus alpha times that term. Okay? I do not pick up any of these other extraneous terms because they're all producing high frequency signals. Can you see that? So I can do a low pass filtering on this signal and will pick up something that is the sum of these two. Okay? And then I can adjust its amplitude, get rid of the DC term very easily. How do you get rid of DC term? You do a notch filter or low pass filter. The capacitor is a very good low pass filter because capacitor does not allow DC signal to go through. So you can pass the signal through a capacitor, the DC term will go away. Okay? And then you have a signal that is looking like your original voice signal, and you don't need a coherent detection. You don't need to adjust something that is properly time delayed and properly having the same phase. It's a very cheap detector. And you can even do it this way. This way is even cheaper than this one. This one needs 1 diode, this one needs 4 diodes. And if you do it that way, then you don't have exactly this signal, but a signal that looks like this. So you still have the envelope. But what happens if you pass this signal through a low-pass filter? Intuitively, I'm not going to go through the mathematical analysis. Mathematical analysis means that you have to Fourier transform this, Fourier analyze it. But intuitively, this consists of a low-frequency signal riding on top of a high-frequency signal. This one too is a low-frequency signal riding on top of a high-frequency signal. And we see that in the mathematics. Low-frequency part riding on top of this high-frequency part. The high-frequency part can be gotten rid of by a low-pass filter. So if I were to pass this signal through a low-pass filter, I will get rid of the high-frequency part and leaving behind the low-frequency part, which is my envelope. Of course, it contains this DC term, and DC term can always be gotten rid of by using a capacitor. Yes? Did I hear a question? No? Okay. So are there any questions on envelope detection? It's pretty straightforward, right? It's duck soup. But it's a piece of cake. Have you figured out what duck soup means? What does hot soup mean? You get hot soup.
What if there's no bugs around your area?
Oh, I don't know. You ask Groucho Marx. He has a movie called Duck Soup. You remember who Groucho Marx is? No. Okay. So there is an even simpler design in the textbook. If you want to do envelope detection, you can do it with this thing. Okay? So if you do something like this, then this part acts like a low-pass filter. Because if this signal comes in, it gets rectified. This is rectified with a rectifier and becomes something like that. Then the high-frequency part will just go through the capacitor. Whatever comes out here that gets connected to your earphone, okay, your earphone looks something like this. And then whatever gets connected to your earphone is just the low frequency part, because the high frequency part will get short circuited by the capacitor. And this is a very simple design of a low pass filter. Okay?
This is what they use in the labs.
What is that?
This is the design they use in the lab.
Oh, okay. Okay, sorry. So you have already done this in your lab, so you are
We're
a pro.
experts.
What is that?
We're experts at it.
You're expert at it, so you know everything that you need to know about this. So then there's a question in the book that asks if envelope detection is a linear process. Is it a linear process? Well, say if I have two signals, F1 and F2, and if this goes through my system simultaneously, then I will modulate it with this thing, and then I will do envelope detection by converting this, and then I try to extract only the amplitude part of the signal. So envelope detection does this. You get rid of this by some low-pass filtering action, and whatever you have finally is the N F1 plus F2. Okay? If I send only one signal through, I get amplitude of F1. If I send the other signal through, I get amplitude of F2. Then does this process satisfy the linearity axiom? Does it? That is the sum of both the same as the sum of the amplitude of the individual? So the question to ask is that F1 plus F2, is it equal to that? Not equal to, right? Not equal to. So in general, it's not a linear process. Okay, it's not a linear process. So let's go to the other one, which is heterodyne detection. Section 8.4. Heterodyne detection. There's something that is very difficult with coherent detection. Of course, you can do envelope detection. You can do this kind of thing. You can actually go to Radio Shack and buy one of such thing and make this simple radio yourself. Have anybody done that before? Okay, so you can go to Radio Shack, make a radio.
Yeah, sometimes I was bored.
Yes. You make an LC tank circuit, Did they connect it to an antenna?
Not yet.
No, okay. Connect this to an antenna. Put this through the diode. And then put it to a capacitor here. And then connect to your earphone. Your earphone is like a resistor. Okay? You can make this very simple radio. And you can change the capacitor with a variable capacitor. So that, say, if AM580 comes in, and you tune this capacitor so that this becomes resonant at AM580, or 580 kilohertz. What happens to this tank circuit when it's resonant? It becomes what does a parallel LC tank circuit become when it's resonant? It becomes an open circuit. Okay? So the signal, the current that comes from your antenna has no way to go back going in this direction, and it goes into your earphone. Okay? But if it's off resonance, then the signal just goes through the LC tank circuit and got short circuited and go to ground. Okay? So this is a very simple radio that you can design. But it's too simple and too cheap. And also very difficult to design if you have AM580, you have AM maybe 600 side by side within. And you cannot distinguish a station from another one very easily. Okay, because the low pass filter design that you have is really lousy. Okay, it's really lousy, and you cannot discriminate different stations. Okay? So in order to allow you to distinguish different stations, you need a very high fidelity and high quality band pass filter, for instance, or low pass filter. Okay? So if you do coherent detection, you can bring the signal back into the pass band as a low frequency band, but in order to get the signal properly passing through your system, you still need a very high quality filter. So if I have AM580 over here, 580 kilohertz, and then that means that the carrier of the station is 580 kilohertz. So this is actually the received signal. Okay? And there might be other stations, radio stations, very close to it. Very close to it. Maybe there's another one around here, another one around here, and then another one around somewhere. And each of these stations has a bandwidth that is pretty narrow. The FCC, the Federal Communication Commission, I think, allows only a very small bandwidth for each radio station. How much do you think they get? They get only about 10 kilohertz, because human hearing is very small. We can hear only about 20 kilohertz. So these stations are not that far apart. They're actually quite close to each other. 580 kilohertz with only 10 kilohertz of bandwidth. So in order to pick up these stations correctly, after you do a coherent detection and bring it down here, you might get the other stations over here. And in order to pick up AM580, you will need a 10 kilohertz bandwidth filter in order to not pick up the other radio stations. Okay? And the other radio stations are extremely close by. So it's not easy to do this at this kind of frequencies, because then you need very high quality filters. Okay, you need very high quality filters to do that. The answer to this problem then is to use heterodyne detection. Okay, this is section 8.4 of the textbook, which is super heterodyne AM receiver. It's super heterodyne. So how does this work? Well, this works in this manner, that you do not demodulate it down to the low frequency. Okay, you do not demodulate it down to that low frequency. You have this signal. First you have a signal. You modulate it. Well, this is a received signal that you will have at the receiver, and it has been modulated, so it has two bands. This is omega C, this is minus omega C. And then when you demodulate it, you don't demodulate it down to the DC band or the very low frequency band. Instead, you pick the frequency so that when you demodulate, you push this to the right one time, you push it to the left another time. You demodulate it to a frequency over here. And then when you push this thing by multiplying by omega carrier, you push it. Let me draw the diagram for you, maybe it becomes clearer. So you have this received signal coming in, and then when you demodulate it with cosine of omega LO t. LO stands for a local oscillator. Okay. LO is not the frequency of the carrier, so whatever that comes out here is called a not properly demodulated signal, but something called MT. Okay. MT would be having a spectrum of something like this. You get pushed by omega L0 to the right, and that how much it gets pushed by. Okay, this is omega LO, the frequency of the oscillator.